Bismillahirrahmanirrahim. In this unit, we will highlight the significance of three mathematical tools that have revolutionized the way we understand and design communication system in science and engineering. Fourier series, Fourier transform, and Laplace transform. Let's start with the Fourier series. This tool allows us to break down any periodic signal into a sum of sine and cosine waves. Think of it as understanding the music of universe. For example, in communication system, a carrier wave used in amplitude modulation or frequency modulation radio is periodic, and Fourier series helps us study how this information modulates the carrier also play critical role in analyzing harmonics, filtering noise, and even compressing image in format like JPEG. Moving from periodic signal, the Fourier transform take us to the realm of the aperiodic signal, converting them from the time domain to the frequency domain. This transformation is the backbone of modern signal processing, and as well as communication systems. It helps engineering analyze the spectrum of signal, design filters, and even enable technologies like Wi-Fi, 5G, and radar. In these systems, the Fourier transform allow us to separate and process signal in a communication system without interference, ensuring reliable communication. Lastly, we will discuss about Laplace transform in this unit. Laplace transform take the Fourier concept a step further by enabling us to analyze system in both transient and steady states. It's valuable in control system, circuit design, and communication stability of electronic communication system. For example, when designing a feedback loop in a receiver or stabilizing a wireless signal, the Laplace transform provides a clear view of system behavior in complex frequency domain. Together, these tools allow us to analyze, design, and optimize everything from cellular phone network to the medical imaging system. They are not just mathematical abstraction, they are the language of technology. A periodic signal repeats itself over a fixed interval called the time periods, as shown from the figure. And example includes square wave, sawtooth waves, and sinusoidal signal. Modulating signals are periodic signals. So that's why we will have a lot of application of Fourier series for the communication system and especially amplitude modulation, phase modulation, and frequency modulation. Harmonics are sinusoidal component of the signal whose frequencies are integer multiple of the fundamental frequency. Do we see that? First, first signal, which has a large time period, it has a frequency f naught. All other frequency are integer multiple of that frequency. This concept helps us for filtering out the spatial frequency component from the signals. The fundamental frequency is the reciprocal of the signal period f naught is equal to 1 over t naught. And now we discuss about the decomposition. Fourier series break the signal into main two components. One is DC component representing the average value of the signal, and then a series of sine and cosine term representing the oscillating component at higher frequency. Now we discuss about the mathematical equation of Fourier series. Actually, any periodic signal can be represented by mathematically by fx with a time period t. The Fourier series expression can be written as fx is equal to a naught summation from n is equal to 1 to infinity and bracket start an cos 2 pi nx divided by t bracket close plus bn sine bracket start 2 pi nx over t bracket close and all bracket close. Now here a naught is equal to 1 over t integration from minus t by 2 to the t by 2 fx dx, and which is a DC component. And similarly, the an, which is can be written as 2 by t integration from minus t by 2 to the t by 2 fx cos 2 pi nx divided by t dx, which is a cosine function. And similarly, Bn, which represents the sine function, amplitude of the sine function, is equal to 2 by t integration minus t by 2 to 2 by 2 and fx multiplied by sine 2 pi nx divided by t dx. Now the Fourier series decompose the signal into harmonics. And first harmonic, as shown in the figure, the fundamental frequency component we have already discussed in the previous slide. Second harmonics is basically oscillate at twice the fundamental frequency. And third harmonics oscillate three times the fundamental frequency and then carry on three times, four, five, six, seven, eight, nine, 10, and go on. Their amplitude is so small that we can nearly negligible. So we can say that each harmonic contribute a specific amplitude and phase to the overall signal. We will consider only such harmonics whose amplitudes are reasonable because they are multiplied by the cosine function. These contributions are quantified by AN and BN. Now we discuss about the mathematical equation of Fourier series. Actually, any periodic signal can be represented by mathematically by fx with a time period t. The Fourier series expression can be written as fx is equal to a naught summation from n is equal to 1 to infinity and bracket start an cos 2 pi nx divided by t bracket close plus bn sine bracket start 2 pi nx over t bracket close and all bracket close. Now here a naught is equal to 1 over t integration from minus t by 2 to the t by 2 fx dx, and which is a DC component. And similarly, the an, which is can be written as 2 by t integration from minus t by 2 to the t by 2 fx cos 2 pi nx divided by t dx, which is a cosine function. And similarly, Bn, which represents the sine function, amplitude of the sine function is equal to 2 by t integration minus t by 2 to 2 by 2 and fx multiplied by sine 2 pi nx divided by t dx. Now the Fourier series decompose the signal into harmonics. And first harmonic, as shown in the figure, the fundamental frequency component we have already discussed in the previous slide. Second harmonics is basically oscillate at twice the fundamental frequency. And third harmonics oscillate three times the fundamental frequency and then carry on three times, four, five, six, seven, eight, nine, 10, and go on. Their amplitude is so small that we can nearly negligible. So we can say that each harmonic contribute a specific amplitude and phase to the overall signal. We will consider only such harmonics whose amplitudes are reasonable because they are multiplied by the cosine function. These contributions are quantified by AN and BN. Now we solve an example of Fourier series where fx can be represented as 1 from 0 to 0 to pi and minus 1 where x from pi to 2 pi and repeated periodic with time period is equal to 2 pi. Up now we draw the graph for the same data. Here the plot of the periodic signal fx as described in the example. The signal alternates between plus 1 and minus 1 for interval of 0 to 2 pi, repeating every 2 pi. The graph illustrates the square wave nature of fx in radians. Here, x-axis is in radians. So 2 pi is equal to, basically pi is equal to 3 by 1, 3.142. So you will see that it is 1 at 3.142. And later on, 2 pi is equal to 2 multiplied by 3.142. So in this way, you will see the x-axis in radians, which is commonly encountered in digital signal processing and Fourier series. Now we solve the previous example. In the first step, we will prove that if the signal is a periodic or not. The very simple way, W naught is equal to 2 pi over capital T, and above from the above signals, it is given that capital T is equal to 2 pi, so omega naught is equal to 1, which is integer. It clearly shows that the signal is a periodic signal. Now in the step 2, we will write the formula of the Fourier series. As we have already discussed that fs can be written as a naught plus summation n is equal to 1 to infinity bracket start an cos nx plus bn sine nx and bracket close, where n is the number of harmonics. It must be 1, 2, 3, 4, and so on. Now, how we determine the amplitude of the DC component, cosine component, and sine component? By a very simple equation. A naught is the amplitude of the DC component, which can be determined 1 over capital T and integration from 0 to t fx dx. And similarly, an is equal to 2 by capital T and integration from 0 to capital T fx cos nx and dx. And similarly, bn can be calculated by 2 by t and integration from 0 to capital T fx sin nx and dx. In the next step, we will evaluate each component one by one. Now in step 3, we will calculate A naught, which is a DC component, and step 2, we see that A naught is equal to 1 over 2 pi 0 to 2 pi fx dx. Now we enter the value of fx because we defined fx from 0 to pi 1 and from pi to 2 pi minus 1. So we divide our integration into two parts, and a naught is equal to 1 over 2 pi bracket start, and first part, which is plus 1, we have an integration from 0 to pi fx is equal to 1 and integrate with respect to dx. And now plus bracket second integration from pi to 2 pi, and fx value is minus 1, and we integrate with respect to dx. Now what happened here that when we integrate 1, it is simple x, and when we incorporate the value of x from pi minus 0, so it is just a pi. But in the another bracket, which is pi to 2 pi, when we incorporate the value of fx minus 1, then 2 pi minus y is equal to 1 pi. So it is here that our equation is a naught is equal to a naught is equal to 1 over 2 pi minus pi. This pi, because here pi minus 0, so this is pi, and here pi minus pi is equal to 1 pi, but this minus sign, it is minus pi. So pi minus pi is equal to 0. So it means that a naught is equal to 0. It means that there is a non-DC component. And it's apparently look like, because there is a balance plus 1 and minus 1, when we take average, it is a 0. Now we in step 4, we will determine the coefficient of cosine and sine function. Now we will determine the coefficient of cosine function, which is n, an. So an we have already discussed in step 2 that an is equal to 2 over 2 pi, which is capital T. So it is 2 pi, and because it is a balance, so we take from 0 to 2 pi fx and cos nx dx. Now to cancel, so an is equal to 1 over pi, integration from 0 to pi, and fx is equal to 1 because we have to convert it to two components from 0 to pi and pi to 2 pi, and fx value from 0 to pi is equal to 1. So our integration is simple, cos nx plus minus cos nx here. Now we, because we cannot cancel out because the integration limits are different. Here integration limits from 0 to pi, and here it is pi to 2 pi. So we cannot cancel out. Although it is also cosine x, it is also minus cosine x, but due to the difference of the limit, we cannot cancel out. But later on, we know that when we integrate from 0 to pi and cos s nx is equal to sine nx, and x is the coefficient to come into the denominator. And when we apply limit from pi to 0, so sine n pi minus sine and 0. And 0 is a 0. Problem is that pi is equal to 180 degree and sine value of 180 is 0. And similarly, sine 0 is also 0. So our cosine function is equal to 0. Now here we also cosine function for this limit is equal to 0. Now we apply a cosine function for the limit from pi to 2 pi. Again, integration of the cosine nx is equal to sine nx divided by n, and we apply a limit from pi to 2 pi, and firstly we incorporate the limit sine 2n pi minus sine n pi. Now, pi, multiple of the pi is always 0 cosine function here. 2 pi, 3 pi, 4 pi, because it is 2, so 2 pi, 4 pi, 6 pi, 8 pi, they are always 0. And similarly, 1 pi, 2 pi, 3 pi, 4 pi is also 0. So that's why both are 0, so our this function is also 0. So practically an is equal to 0 for all value of the n. In other words, all harmonics, our DC component is 0 and our cosine function amplitude is also 0. Let's see about the coefficient of the sine coefficient in next step. Now in the fifth step, we will calculate the coefficient of sine function. As we know that Bn is equal to 2 over capital T integrated from 0 to 2 pi fx sine nx dx, and capital T is equal to 2 pi. So here 2 cancel and it becomes 1 over pi. Now fx is defined two values. From 0 to pi it is 1, and from pi to 2 pi is equal to minus 1. So we write here from 0 to pi 1 sine nx dx plus pi to 2 pi it is minus 1 sine nx dx. So now what we do here that we will write sine nx is equal to, because these are different values, same sine function but different limits, so it cannot be cancelled out. Firstly we determine this value of integration and later on we determine this value of integration. We apply here sine nx dx, as we know that sine integration is minus cos nx divided by n. We apply the limit from pi to 0, so we write here that cos n pi, because this is n and x is replaced by pi, n pi, and cos n multiplied by 0 to 0, we write here minus cos x. And this minus is a sine integration of the sine to the cosine minus here. Now problem is that cos pi is always be 0. Sorry, cos 0 is always be 1. So that's why we write here firstly is 1. And cos n pi depends on the value of n. If n is equal to even 2 pi, 4 pi, 6 pi, it is plus 1 value. And when n is equal to odd, 1 pi, 3 pi, 5 pi, its value is minus 1. So exactly mathematically it can represent by minus 1 power n. Because n is equal to even, it is plus 1, n is equal to odd, it is minus 1. And here, this is 1 minus bracket start minus 1 power n divided by n. Up now we apply same concept to integration here. They have same value, but limits are different. Again, sin nx dx can be written as cos nx divided by n. And here limits are different from pi to 2 pi. So we apply cos 2n pi minus cos n pi divided by n, and this is the minus sign integration here. Minus sign integration here. This is the uh, integration of the sine function into cosine with minus sign here. Now we apply the limit. And now situation is good thing is that 2 pi is always be plus 2 and pi is always be plus 1. So that's why we write here plus 1, and this minus 1 make it as a minus 1 here. Up now this 1 here, make it minus 1 here, and now we applied this minus and cos and pi. Similar way, cos and pi we write here this value, so we can write here minus 1 power n. And this minus is here, we cannot take as a common. It is wrongly written, this minus here. So now we apply our bn, and we can write here from this one integration plus, so it must be a plus here, it must be a plus here, and this is the this minus here, so we cannot make it like that here. So very similar way, these are the for this integration and this for this integration. Now n values, firstly we use the odd even value, for example, for simplicity 1 minus minus 1 power even, so this become plus 1, and 1 minus plus 1 is 0. Very similar way, I told you that this minus is not here, this minus is here, which is plus. So very similar way, exactly. When n is equal to even, so 1 minus and this value is minus 1, so it become automatically cancel out and they 0. So for n is equal to even, bn is equal to 0. Now we apply for the odd value minus 1 power n, so it's become minus 1, and 1 minus minus 1, it become plus 2 power n. And very similar way, plus 2 power n here, so it become 4 power n. And our equation, very simple way, bn is equal to 1 over n multiplied by the 4 power n. Now finally we can write the equation function fx is equal to 1 from x is 0 to pi, and x from pi to 2 pi can be written in fx is equal to a naught plus an component of the cosine function plus bn component of the sine function, as a naught is equal to 0 and cosine function amplitude is 0. So fx is equal to summation from n is equal to 1, 2, 3, 5, because this is odd, and 4 by n pi sine nx. Now it is much worthful equation as compared to this equation, because it contains lot of information, which is the main purpose of the Fourier series. This series consists of only odd harmonics and is equal to 1, 3, 5 here. And this reflects the symmetry of the original function, because sine function is a purely symmetry about the function. Now we discuss about the amplitude of harmonics. The amplitude of each harmonics is decreases by 1 by n. And if, for example, n is equal to 1, which is 1 over n, simple one, n is equal to 2, so amplitude become 4 pi multiplied by 1 over 2, it become half. So every harmonics, our amplitude 4 by pi is become the half of the previous value. In other words, higher component of frequency amplitude is very small. So it is good practice that if you want to reconstruct the signal, so only few harmonics are enough to reconstruct the signal with the required accuracy. Now we we can say that by summing up enough terms of the Fourier series, we can closely approximate the original square wave function. Such decomposition is used in signal processing to analyze periodic wave like square waves in digital communication, pulse width modulation signal in a control system, and example demonstrate how a complex periodic signal can be broken into simpler sinusoidal component for further analysis and reconstruction. Thank you. Fourier transform is not just a mathematical tool. It is a cornerstone of modern innovation. From your smartphone to space exploration, it is quickly working behind the scene, making the impossible into possible. So the next time you enjoy seamless video streaming or crystal clear phone call, remember that Fourier transform and its profound role in connecting our world. Fourier transform can be defined as a time domain signal xt. The Fourier transform xf is defined as that xf is equal to integration from minus infinity to plus infinity xt e power minus j pi j2 pi ft integrated with respect to time response. Now we define each component here. Xt, the time domain signal, XF, frequency domain signal, which is the purpose to convert time domain signal into frequency domain signal. Here F is frequency in hertz, J is a imaginary unit to represent a complex variable. Signals in communication system are often analyzed and processed in frequency domain because many operations, for example, filtering, modulation, are very simple in frequency domain. Signal characteristics like bandwidth and frequency contents are easier to interpret. However, the real world analysis of the signal are typically in time domain. For example, voice, video, data, etc. So we use the inverse Fourier transform. Simply IFT. The IFT is needed to convert process signal back to their time domain from the transmission or playback. Enable end user or device to interpret the signal in its original form. XT can be calculated, which is in Fourier inverse Fourier transform. XT is equal to integration from minus infinity to plus infinity xf multiplied by j e power 2 pi ft and integrate with respect to frequency domain. The difference between Fourier transform and inverse Fourier transform is that in Fourier transform it is xt and e power minus j 2 pi ft, while in inverse Fourier transform it is xf and multiplied e power j 2 pi ft and integrate with respect to frequency domain. Let's discuss the signal and explore why spectrum analysis, signal transmission, filter design, and modulation are critical to modern communication system and how they are all connected by the Fourier transform. First, spectrum analysis. Every signal we encounter, whether it is your voice or phone call or song you are streaming, has a unique composition of frequency. By analyzing these signals using the Fourier transform, engineers gain a clear understanding of the signal structure and energy distribution. This insight is essential for designing efficient communication systems and understanding noise, interference, or distortion in the real world application. Now, signal transmission, the communication based band signal often needed to be converted to high frequency known as passband signal for efficient transmission over a long distance. This is why Fourier analysis come into, and it allows the transform and optimize the signals and ensuring they can travel across various medium such as cables or wireless network without losing quality or clarity. Moving on the filter design, filters are indispensable tool in communication used to extract or suppress a specific frequency component from the signal. For example, when you are on phone call, noise cancelling algorithm rely on filter to block out background noise, leaving only the desired voice signal. The Fourier transform is critical here, enabling engineers to identify and isolate unwanted frequency for removal. Finally, let's talk about the modulation and demodulation. These processes allow us to transmit data over long distance efficiently. Technique like amplitude modulation or frequency modulation modify a carrier wave to encoding information. Fourier analysis and transform provide the mathematical framework to understand and optimize these techniques, ensuring signal and transmitted and recovered accurately. The Laplace transform is vital for communication systems due to its ability to simplify as well as analysis as well as design of complex communication systems. Here are some key reasons why it is so important for communication system. Most important is that system analysis and design. The Laplace transform converts time domain signal into complex frequency domain signal, making it easier to analyze and design, particularly linear time invariant system. It provides insight into system behavior such as stability, transient response, and steady state performance. Another important is that incorporating initial and final conditions. Unlike the Fourier transform, the Laplace transform can handle signal with non-zero initial conditions. This makes it ideal for analyzing system with memory such as filter, amplifier, and feedback circuit. Another importance of the Laplace transform is to design filter circuits. Communication systems rely heavily on filter types, different type of filter type to process various type of signal. The Laplace transform helps in designing filters by giving a clear relationship between input and output in S domain, enabling engineer to design high performance filter for noise reduction and signal enhancement. Stability analysis. The Laplace transform helps to determine the system stability through pole zero analysis. By examining the location of pole in the S-plane, engineer can design stable communication system that avoid oscillation or under design behavior. Modulation and demodulation. In communication system, modulation is key, often introduce transient component. The Laplace transform capture both transient and steady state response, making it suitable for analyzing modulation technique like amplitude modulation, phase frequency modulation, or digital modulation. The most important is transfer function design. It is used to derive transfer function which represent the input output relationship of the system, in the S domain for many electronic circuits which are used in communication. This simplifies the design and analyzes the circuit like oscillators, modulators, and demodulators. Another important application of Laplace transform is to circuit design for the analog communication circuit. For analyzing communication circuit, maybe analog or maybe digital, the Laplace transform allows engineers to work with complex impedance in the S domain, making it easier to solve differential equation and understand frequency dependent behavior of the circuit.